Welcome to the first of two narrated PowerPoint videos for Lecture 3. In this presentation, Section 1, I will cover uncertainty analysis. In Section 2, I will cover calibration. Uncertainty analysis builds on the concept of measurement uncertainty covered in Lecture 2, Section 3. Measurement uncertainty tells you and your report readers the uncertainty associated with a measurement in terms of a plus-minus value. Recognizing that every measurement has some uncertainty, an important question that comes to mind is what is the combined impact of all those measurement uncertainties on a calculated result? How do you determine the uncertainty of a calculated value that uses multiple measured values when each measurement has some uncertainty? The purpose of uncertainty analysis is to calculate an uncertainty of a calculated result that involves multiple measured values in the equation, and each measured value has a measurement uncertainty. For example, the ideal gas law can be used to calculate the number of moles added to a rigid container by microbial action by measuring the change in pressure and knowing the rigid container volume above the biologically active liquid and the temperature. The equation involves three measured values: the pressure change delta P, the rigid container volume above the liquid V, and the temperature T. And each measured value has some measured uncertainty. The universal gas constant R is a constant and it does not have any uncertainty. Here is the ideal gas law and some of the information we will need to do an uncertainty analysis. We need the equation, a typical measured value for each variable, and the measurement uncertainty for each variable. For this example, which I will complete later, the typical measured pressure change delta P is 20.0 kilopascals plus or minus 0.05 kilopascals. The container volume V is 0.40 liters plus or minus 0.01 liters. The absolute temperature T is 300 degrees Kelvin plus or minus 2 degrees Kelvin. R, the universal gas law constant with the appropriate units, is 8.314 liter kilopascals per gram mole degree Kelvin, and there is no measurement uncertainty. The purpose of the uncertainty analysis is to quantify the uncertainty of a calculated value using multiple measured values, each with measurement uncertainty. We can get three useful pieces of information from an uncertainty analysis. First, it can quantify the uncertainty of the calculated result R, so that we have a result R plus or minus the uncertainty of delta R. Second, we can use uncertainty analysis results to identify which measured value uncertainty contributes the most to the result uncertainty delta R. This information can be used to identify which measured value is the first one, the most critical one, to reduce if we want to reduce the result uncertainty. So for the ideal gas law example, do we need to measure temperature more precisely, or the container volume, or the pressure difference? Third, we can use uncertainty analysis if we work backwards, knowing the maximum uncertainty allowed, to figure out the maximum uncertainty of each measured variable. We will not be doing this in class. We can calculate two different types of error, which we will later turn into uncertainties. One is the absolute error. The absolute error gives us the maximum error by adding the absolute error of each measurement. This is the worst case and is not commonly used because it is the worst case, which is unlikely to occur. The second error is the root sum square error. This is the more practical one to use. The approach for calculating both the absolute error and the root sum square error is similar. Both start with a Taylor series expansion. Here is a general Taylor series expansion for two variables x and y. For each variable x and y, there is a corresponding uncertainty dx and dy, which correspond to the plus-minus uncertainty values for the measurements of x and y. We can write r plus delta r equals r plus the partial of r with respect to the partial of x times dx plus the partial of r with respect to partial y times dy plus 1 over 2 factorial times several higher order terms in the square brackets. We are interested in delta r, where delta r corresponds to the plus-minus uncertainty value. If we assume that dx and dy are small, which we generally do for random errors of each measurement of x and y, then we can neglect the higher order terms in the square brackets. After neglecting the higher order terms, we subtract r from both sides to get delta r equals the partial of r with respect to the partial of x times dx plus the partial of r with respect to the partial of y times dy. This is the expression for equations with two measured values, x and y. The process can be expanded to handle more measured variables. This slide shows how we define absolute error for two variables x and y. We will use epsilon subscript a as the variable to describe absolute error. Using the previous expression for delta r for two variables x and y, we define the absolute error as the sum of the absolute values of the products of the partial of r with respect to the partial of x times dx plus the partial of r with respect to the partial of y times dy. The absolute value eliminates any negative values and produces the maximum error. By inspection, we can see that this expression can be expanded for the general case with n variables as written here. This gives the absolute error. This slide shows how we define the root sum square error. We will use epsilon subscript rss as the variable to describe the root sum square error. The root sum square error uses the same partial terms and dx or dy terms used for the absolute error. But instead of summing the absolute values, we square the individual products, sum them, and take the square root of the sum of the squared terms. Squaring the terms takes care of any negative values again. So to find either the absolute error or the root sum square error, we need to start by taking partial derivatives of the equation with respect to every measured variable in the equation that has a measurement uncertainty. You may find the 13 differential formulas given in the course packet on page 3-3 useful as you take partial derivatives. It is easy to make mistakes taking partial derivatives. One quick way to check to see if you are doing your partials correctly is to check the units of each. You should get the same units as the original equation. So let's go back to the ideal gas law example. We want to find the uncertainty of n using the root sum square error. We need to know both typical values of each variable and the uncertainty of each measured variable. These measurement uncertainties may be given, or you may need to get them from specification sheets of each sensor used. In this problem, the typical delta P pressure is 20.0 kilopascals, and the pressure measurement uncertainty is plus or minus 0.05 kilopascals. The rigid container we are using has a volume of 0.40 liters, and the volume measurement uncertainty is plus or minus 0.01 liters. The typical temperature is 300 degrees Kelvin with a measurement uncertainty of plus or minus 2 degrees Kelvin. The universal gas constant value is 8.314 liters kilopascals over gram mole degrees Kelvin, and it does not have any uncertainty. This slide shows the partial derivatives of the ideal gas law with respect to each variable delta P, V, and T times the derivative of the measured variable. This is a good time to do a units check of our partial derivatives. When we put in the units for each term, the results are all the same, moles. While this does not confirm that our partial derivatives are correct, it does give us confidence in them. The next step is to plug in the typical values and the correct measurement uncertainty given in the previous slide. Note that d delta P is the uncertainty of the pressure measurement, 0.05 kilopascals. dV is the uncertainty of the volume measurement, 0.01 liters, and dt is the uncertainty of the temperature measurement, 2 degrees Kelvin. After plugging in the numbers, the results for each term are 8.019 times 10 to the minus 6, 8.019 times 10 to the minus 5, and 2.138 times 10 to the minus 5. One of the things that these results tell us is that the measurement uncertainties for the volume and the temperature have the same order of magnitude, 10 to the minus 5. They are both roughly an order of magnitude larger than the value for the pressure measurement. The volume uncertainty contribution is larger than the temperature uncertainty by roughly 4 times. This means that if the final uncertainty is too big, these are the two measurements to work to reduce their respective measurement uncertainties. It would not be a good idea to try to reduce the pressure measurement uncertainty. The other two measurements have a much bigger impact on the final uncertainty result. To find the root sum square error, we plug in the results from the previous slide, square each term, and sum them, and take the square root of the sum to get 8.34 times 10 to the minus 5 moles, which can be written as 0.0834 times 10 to the minus 3 moles. Using the typical values, we find that the number of moles added to a rigid container with a 20.0 kilopascal pressure change is 3.21 times 10 to the minus 3 moles, plus or minus 0.08 times 10 to the minus 3 moles. Note how I round the results to have the same precision. The class notes describe the ideal gas law problem for the absolute error, and there's an additional example you can look at. Remember, uncertainty analysis can tell us 3 things. It can tell us the uncertainty of the calculated result using multiple measured values, 0.08 times 10 to the minus 3 moles in this example. It can also tell us which measurement contributes the most to the uncertainty, volume then temperature in this example. Finally, it can tell us the allowable error of each measurement. This was not done here or in the notes because it involves trial and error, but it can be done. This ends the narrated presentation for Lecture 3, Section 1, where we covered uncertainty analysis. Next time I'll talk about calibration. Please write down any questions you have and bring them to class.